Hello everyone. Welcome to today's session. This session is on machine learning for cancer detection. Over the next several hours, we are going to go from the every basics of what cancer is, all the way through hands-on machine learning algorithms, deep learning models, and model evaluation and explainability, specifically applied to three cancers that are blood cancer, cancer, and skin cancer. The slides are well defined, so you can go through it anytime. And if you have any questions along the way, you can always reach out to us at biotechrebion@gmail.com. Let's get started. Here's our roadmap for today. We have organized it into six parts, like covering 35 concepts in total. Like part one covers the foundations, what cancer is, why early detection matters, and quick overviews of three focus cancers, that is blood cancer, breast cancer, and skin cancer. Yes. And then part two is about data and pre-processing, where it will be showing that where the data comes from and how we can clean it. Part three is the big one, that is supervised learning algorithms, where we'll go through eight different ML models in detail. Then comes part four, where we'll be covering deep learnings and cancer models, including image based analysis. And in part five, it's about evaluation and explainability, like how we know if a model is actually good and how we make it trustworthy. Okay. And in part six, it's a wrap up with real clinical applications, honest challenges, and where the future is heading. Uh, I would recommend treating each part as its own sitting rather than trying to cover all six in one go. Okay. So let's go further. Let's begin with part one, that is foundations. In this part, we will build our shared vocabulary, that is, what cancer actually is at a cellular level and why timing matters so much in detection, like a refresher on what machine learning even means, and quick overviews of blood, breast, and skin cancer specifically. Yes, now let's start right at the beginning. Cancer isn't one disease, yeah? It's a name we give to a whole family of diseases where something goes wrong at the cell level. Every cell in your body normally follows a life cycle. That is, it grows, it divides when needed, and it dies when it's supposed to. Cancer happens when a cell's DNA gets damaged. That is, it can be through a mutation, and it stops listening to those stop growing or time to die signals. It just keeps dividing uncontrollably, forming a mass of abnormal cells. Yes, so there isn't just one type either. There are over 200 plus recognized types classified by where they start, like carcinomas in glandular tissue or sarcomas in bone or muscle, leukemia in blood forming tissue, and lymphomas in the lymphatic system. Risk factors range from genetics you are born with to things like smoking, radiation, chronic infections, or diet. The reason we are spending an entire session on this simple cancer remains one of the leading causes of death worldwide. And one of the biggest levers we have to change what that outcome is catching it early. Let's have an example. Just think of a single cell, like a factory worker who normally clocks in and does its one of the task and clocks out when told. A cancer cell is like a worker who ignores every instruction from management and just keeps working overtime forever, taking up more and more space and resources. Getting? Now, why are we obsessing over early detection specifically? Because cancer has stages and survival rates change dramatically depending on which stage you catch it at. If a cancer is caught at stage 1, it might be small and hasn't spread. 5-year survival rates for many cancers are above 90%. If the same cancer isn't caught until stage 4, when it's spread to the other organs, that number can drop drastically. Beyond survival, early detection also means simpler treatment. Removing a small tumor is very different from months of aggressive chemotherapy. Yes, the problem is traditional detection tools, that is, biopsies or imaging, lab tests, while accurate, can be slow, expensive, and sometimes subjective. That is, two doctors might read the same scan differently. This is exactly the gap machine learning steps into. That is, it can look at thousands of data points faster than a human and flag high risk cases early and do it consistently every single time. Let's understand this with an example. Uh, Let me think. Yes, it's like we can say a smoke detector. If it beeps the moment there's a little smoke, you put out the fire in 10 seconds. If it only beeps once, the room's fully on fire. You are calling the fire department instead. Early detection is the smoke alarm going off early. Before we go further into cancer, let's ground ourselves in what machine learning actually is, since we will use this vocabulary all over the session. Traditionally, if you wanted a computer to do something, you would write explicit rules. Yes, like for example, if X happens, then do Y. Machine learning flips that. Instead of writing the rules ourselves, we give the computer a lot of examples and it learns through the rules on its own by finding patterns in that data. There are three broad flavors, that is supervised learning. It is when we give the model labeled examples like the tumor is benign or malignant, and it learns to map inputs to that label. Unsupervised learning is when there are no labels and the model just finds natural groupings. Third, that is reinforcement learning. It is when a model learns through trial and error, getting rewards or penalties. For essentiality, everything in this course, we are doing supervised learning because we have historical patient data where we already know the diagnosis and we want the model to predict that diagnosis for new patients. Yes, let's have an example. Let's say it's like teaching a child what a dogs look like. Instead of describing every breed with rules, you just show them 100 photos labeled dog and 100 labeled not dog. Eventually, they figure out the pattern themselves. That's called supervised learning. Getting? In ML research specifically, cancer data generally comes into flavors, and this distinction matters a lot for which techniques we use. The first is a structured or tabular data. That is, Think of a spreadsheet where each row is a patient and each column is a number, uh, like a lab measurement or cell size. The second is image data, that is actual pictures like scans or microscope slides. In this course, we are covering three cancers picked deliberately because each represents a data type. Blood cancer typically uses tabular lab value data. Breast cancer is a nice hybrid, that is, it has both famous tabular dataset and image based mammogram data. And skin cancer is almost entirely image based since diagnosis relies on looking at the lesion. By the end of this session, you will have seen ML applied to both data types. Let's understand this with an example. Uh, Imagine there are three detectives solving three different crimes, like one only has financial records, that is pure numbers, one only has crime scene photographs that are pure images, and one has both, that's blood, skin, and breast cancer in that order. Now, let's zoom into blood cancer. What is blood cancer? Blood cancers are, it can be leukemia, lymphoma, myeloma. It starts when something goes wrong in how your body produces blood cells, usually inside the bone marrow, your body's blood cell factory. Doctors diagnose this mainly with a complete blood count or CBC, that is measuring white blood cell count, red blood cell count, and platelet count. If the white blood cell count is unusually high or cell look structurally and abnormal under a microscope, that's a red flag. Confirmation often comes from examining a blood smear, that is a thin layer of blood on a glass slide, that is under a microscope, or from a bone marrow biopsy. For our ML purposes, this means two parts, that is, train a model on numeric CBC values or train a model to look directly at microscope images of the blood smear and spot abnormal cells visually. Yes, we can understand this using an example, like you can just think of your bone marrow as a cell factory with a strict production quota. In leukemia, the factory goes rogue and overproduces broken, non functional white blood cells, flooding the warehouse, that is your bloodstream, with defective inventory that crowds out the healthy cells doing real work. Getting? Now, breast cancer is probably the most well studied cancer in the entire ML literature. Yes, which is why it's a great starting point for hands on practice. It develops in breast tissue cells, and while it's far more common in women, it can occur in men too. Diagnosis typically starts with a mammogram followed by a ultrasound, and if something looks like suspicious, a biopsy where cells are physically extracted and examined under a microscope. Here's the part that matters most for us is when pathologists look at those biopsy cells, they measure specific physical properties, that is, the radius of the cell nucleus, its texture, parameter, and how smooth or jagged its order is. These measurements were digitized into a famous dataset called the Wisconsin Breast Cancer Dataset. That is the exact dataset we use for the demonstration. The model's goal is simple, that is, given these measurements, predict whether the tumor is benign or malignant. Let's consider uh, Picture two circles on a paper. One is smooth and perfectly round, roughly what a benign cell nucleus looks like. The other has jagged, uneven edges closer to a malignant one. The Wisconsin dataset turns how jagged is this shape into a number the model can use. Skin cancer is our third cancer type and it's fundamentally different because diagnosis is almost entirely visual. That is, it happens when DNA damage, most commonly from UV exposure, or causes skin cells to grow abnormally. The most dangerous form is melanoma because it can spread quickly if not caught early. Dermatologists use the ABCDE rule to visually assess a mole, that is, say, asymmetry, that does on one half not match the other. Border is the edge irregular and color, that is multiple colors instead of one. Diameter, that is larger than about 6 millimeters and evolving, that has it changed recently? Because diagnosis is visual, the primary ML data source here is dermoscopic images, zoomed in, well lit photographs of the lesion taken with a specific special magnifying device. Yeah, so let's have an example. It's the same instinct as checking if a coin is counterfeit. That is, you are not measuring its weight with lab equipment. You are visually checking, is the edge uneven? Is the color off? Does something just look wrong compared to a normal coin? And so on. Yes, so you can see here are the some of the images of skin cancer, how it looks. What do the ABCDs of skin cancer stand for? A is for asymmetry, B is for border, C is for color, D is for diameter, and E is for evolving. We have already covered this, yes? So you can see different types of skin cancers. This part could be a squamous cell carcinoma. These are normal moles, and these are melanoma. See, you can see asymmetry, border, color, diameter, evolving. Now, yes, let's get back to our slide. Now let's have an overview of the data set. Yeah, so this is the data set for breast cancer. You can see I have opened it in Excel. It is a CSV file. We'll be using this data set in our breast cancer model. So in all, there are 570 entries. Okay, let's get back to our slide. Now that we have understand the why, let's move into part 2, that is data and pre-processing. This is the unglamorous but essential foundation every model depends on. Yes, it's where cancer data actually comes from and how we clean and prepare it before any algorithm ever sees it. Yeah. So, where does all this data actually come from? Yes, for breast cancer, there's the Wisconsin breast cancer dataset. We just looked over it. Yeah, it's even built directly into Python's scikit-learn library that is loadable with a single line of code. For broader cancer statistics, there is SEER run by the US National Cancer Institute. So, for skin cancer images, the go-to source is the ISIC archive, and for blood cancer, there is a CNMC built specifically for classifying leukemia cells in microscope images. When working with any of these, watch for missing values, class imbalance, far more healthy examples than cancer examples, and sometimes mislabeled samples. And because this is patient data, there are ethical obligations too. That is, data must be anonymized and comply with privacy regulations like HIPAA before it's shared publicly. Let's just think of these data sets like ingredients in a recipe. Wisconsin gives you the numeric ingredients for breast cancer. ISIC, the visual ingredients for the skin cancer. CNMC, the visual ingredients for blood cancer. That is, good results start with good and clean ingredients. Now, something that sounds unglamorous but is honestly where most of real ML projects time goes. That is pre-processing. Raw data is almost never ready to feed straight into a model. For numeric data, we handle missing values through imputation, that is, filling gaps with something reasonable like the column average. We remove duplicates and outliers and normalize the numbers so every feature is on a comparable scale. For image data, we resize every image to the same dimensions, normalize pixel values, remove noise, and often use augmentation, that is rotating, flipping, or zooming existing images into to create more training data. And there's one very medical specific issue, that is class imbalance. In real data sets, healthy patients vastly outnumber cancer patients. So, we use techniques like SMART to synthetically balance the classes so the model doesn't just learn to always guess healthy. Now, here, SMART stands for Synthetic Minority Oversampling Technique. That, that is, it is a data pre-processing algorithm used to resolve class imbalance in machine learning datasets. It works by generating brand new synthetic examples of the minority class rather than simply duplicating existing records. Yes. Now, just imagine a grading exam papers handed to you in wildly different formats. That is, some in inches, some in centimeters, some upside down, some with pages missing. Here, preprocessing is standardizing every paper into same format before you even start grading. Yes. Now, once your data is clean, the next question is which features actually matter. In the Wisconsin dataset, for example, we have 30 different measurements per patient, but not all 30 are equally useful. Feature selection identifies and keeps the most useful inputs, giving three benefits, that is, better accuracy, since noisy irrelevant features can confuse a model, and faster training, since fewer inputs mean less computation, and confusing one. So, common techniques include correlation analysis and tree based models like random forest, which naturally rank features by importance during training. In our breast cancer dataset, specifically, features like worst radius and worst concave points consistently turn out to be some of the strongest predictors. For example, if you are predicting whether a student will pass an exam, their study hours and attendance are probably very predictive. Their favorite color, while technically data probably tell you nothing useful, right? Like feature selection throws out the favorite color columns and keeps the study hours columns. Okay, now welcome to part 3, that is the algorithmic core of this course, supervised learning algorithms. We are going to go through 8 different models one by one, building from the simplest and most interpretable up to more powerful, more complex ones. We have covered the data side. From here, we shift into the actual algorithms that learn from this data. As a refresher, supervised learning means we give the model labeled training examples of patient's features paired with the known diagnosis, and it learns the relationship between the two. In cancer prediction, this is almost always a classification problem, that is, predicting a category like malignant or benign rather than a continuous number. Before training, we always split our data into a training set, yes, which the model learns from, and a testing set that is held back to check performance on data it's never seen before. Over the next several slides, we will walk through the major algorithms used for this, starting simple and building up in complexity. Yes? Our first algorithm is logistic regression. Despite the name, it's used for classification and not predicting continuous numbers. The model takes all your input features, multiplies each by a learned weight, reflecting how important that feature is, and adds them up and passes that sum through a function called a sigmoid, which squashes the result into a probability between 0 and 1. Above zero point 0.5, we predict one class, below the other. What makes it a great starting point is its interpretability. That is, you can look at the learned weight for each feature and see whether it pushes predictions toward malignant or benign, and by how much. In fact, in our own breast cancer, logistic regression came out as our best performing model with over 99% of ROC AUC. Its main limitation is assuming a fairly linear relationship between features and output. Let's understand this with an example. Just think of it like a college admissions officer with a simple scoring system, that is adding points for a GPA, adding points for test scores, and subtract points for a bad reference letter. Sum it up, and if the total crosses a threshold, you are in. Okay, that's exactly what logistic regression does. Yeah. So next is support vector machine, or SVM. Picture your patient data plotted as points in space, where malignant cases cluster in one area and benign cases in another. SVM finds the best possible line, or in higher dimensions, a hyperplane that separates these clusters, specifically the one that maximizes the margin The distance between the line and the nearest points from each group, a wider margin usually means better generalization to new patients. SVM also has a trick called the kernel, that is, letting it handle cases where data isn't cleanly separable by a straight line. It can be bending the boundary into curves. SVM performs very well on dataset like ours, that is high dimensional but not too huge. The exact profile of tabular cancer datasets. The trade-off is that it scales less gracefully to very large datasets and is a bit more of a black box than logistic regression. Just imagine setting up a fence between two neighboring properties, placing it not just anywhere between them, but also as far as possible from both houses, that is, maximum distance placement, fair to both sides, is exactly SVM's philosophy. Let's just look over it. So here you can see this is the hyperplane that is called also called decision boundary. Here they have said red color is class 1, blue color is class 2, and this line are called supporting vectors. And this is a non-linear SVM. This is linear SVM. Let's understand it more clearly. This gap is known as margin, that is the gap between decision boundaries and hyperplanes. These are supporting vectors. This is your hyperplane for second class. This is your decision boundary. And this is your hyperplane for first class. Okay. Now data transformed with SVM. This is your kernel, right? Now let's get back to our PPT. See here various types of SVM you can see. Class 1, class 2, class 3, they have marked with triangles, square and cross. This is your first strategy. Yes. Now let's get back to our slide. A decision tree works exactly the same way its name suggests. Like, honestly, the way doctors often already think. That is, it asks a series of yes or no questions about the data, and each answer branches you down a different path until you reach a final decision. For example, uh, is the worst radius greater than some threshold? Keep asking questions like this until you arrive at prediction. Yes, the huge advantage is interpretability. That is, you can literally draw the tree and walk someone through exactly why the model made a call, which matters anonymously in medicine. The downside, that is, a single deep tree tends to overfit. Hence, it gets so tailored to training data that it fails to generalize. That weakness is exactly where random forest and XGBoost exist. They combine many trees to fix this. You can understand this with the analogy, like it's basically a flow chart a doctor might follow. That is the cell nucleus larger than average? If yes, then is the border regular? If yes, then likely malignant, or decision tree just learns the best version of that flowchart automatically from the data. Yes. Now, random forest solves the decision tree's overfitting problem with a simple but powerful idea. That is, instead of building one tree, it builds hundreds, each trained on a slightly different random subset of data and features. Then let them vote. Each tree casts a vote for malignant or benign, and the majority becomes the final prediction. Because each tree sees slightly different data, their individual mistakes tend to cancel out when averaged, making random forest far more robust and accurate than any single tree. As a bonus, it gives you feature importance scores for free, exactly what we used earlier for feature selection. This is one of the most widely used algorithms in cancer classification research because it balances high accuracy with reasonable interpretability. For example, it's the wisdom of the crowd. That is, just ask one doctor for a diagnosis. They might have a blind spot. Ask 200 doctors independently and go with the majority. You are far or less likely to be wrong. That's random forest. XG boost, that is extreme gradient boosting. It takes a different approach to combining trees than random forest. Instead of building trees independently and averaging, XGBoost builds trees sequentially, where each new tree is specifically trained to fix the mistakes of the previous ones. It's a chain of trees, each correcting the errors of the one before it. This boosting approach tends to produce extremely high accuracy on structured tabular data. So much so that XGBoost dominates ML competitions on platforms like Kaggle and is a staple in real medical ML pipelines. It has built-in regularization to prevent overfitting and handles missing values automatically. For cancer prediction, it's commonly used both for blood cancer classification from lab values and breast cancer prediction from tumor features. Think of a team of students correcting a group essay in rounds. The first writes a draft, the second doesn't start from scratch. That is, they fix what the first got wrong. The third fixes what's the still wrong after that. Each round, the essay gets more accurate. This is how XGBoost works. KNN, that is K nearest neighbors, might be the most intuitive algorithm we cover. Yes, to classify a new patient, KNN looks at the K most similar patients already in the training data. That is, similar based on feature values and takes a majority vote among their diagnoses. Set K to 5 and it finds the 5 most similar past patients and goes with whatever the majority were diagnosed as. There's no real training phase. KNN just stores the data set and does all its work for prediction time, sometimes for lazy learning. The main design decisions are working the right K, are choosing the right K, and how you measure similarity. Most commonly, Euclidean distance. KNN works well on moderately sized, well scaled datasets, but slows down on very large ones since it compares a new patient against every stored patient each time. Understand it like it's like a doctor thinking, this patient's symptoms remind me a lot of 5 other patients. I have treated four of them and turned out to have condition, say X. So I lean toward diagnosing this patient with X2. Okay, this is how KNN works. Naive Bayes is a probability based classifier built on Bayes' theorem, a fundamental rule about updating beliefs given new evidence. It calculates the probability a patient is malignant given their feature values by combining the individual probability contributions of each feature. It's called naive because it assumes all features are independent of one another given the class. That is rarely perfectly true, since cell size and perimeter are obviously related. But even that flawed assumption, naive Bayes still performs remarkably well in practice, and it's extremely fast to train, yes, even on small data sets, which made it popular in early medical ML research. Because of its speed and simplicity, it's often used as a quick baseline to compare more sophisticated models against. Let's have an example. Just imagine guessing someone's nationality from three independent clues. That is, the language they speak, the currency in their wallet, and their passport color, and multiplying together how likely each clue is per country. Even though these clues aren't perfectly independent, that's the naive trade off, and it still gets a surprisingly good guess. Now, we step into a genuinely different family of models, that is, artificial neural networks, loosely inspired by how neurons in the brain connect and fire. An ANN is built from layers of small computational units, that is, neurons, which are connected to each other. Data enters through an input layer where each neuron represents one feature. It passes through one or more hidden layers where the network combines and transforms the data in increasingly complex ways and reaches an output layer, producing the final prediction. Each connection has a loaned weight, similar in spirit to logistic regression, but stacked across many layers. What makes ANNs powerful is the activation functions like ReLU or sigmoid applied at each neuron, introducing nonlinearity. Yes, sigmoid function, like activation functions, are used for introducing nonlinearity. So without it, no matter how many layers you stack, the network would behave just like logistic regression. Hence, activation functions are important. Now, what's the trade-off? The trade-off is that ANNs typically need more data and compute power than the classical models we have covered. Just imagine of an ANN like an assembly line with multiple stations, say raw materials, your input features go in at the first station, and each subsequent station transforms and combines what came before something more refined until the final station produces the finished product, the prediction. Yes, yes. So here you can see the activation functions. The first one is unit step, that is heavy side. Its graph is like this. It's just like a step function, and its equation is you get zero value when your threshold is like whatever value you get is smaller than zero. Z equals to 0, then zero point 0.5, and Z is greater than 0, then 1. Examples are also given, perceptron, variant, and all. Next is our sine function. So you can just go along this, like you will be getting here -1, 0, 1. Next is our linear activation function, where phi of z equals to z. It can be used as Adeline or linear regression, then piecewise linear, then logistic sigmoid, hyperbolic tangent. See here, the graphs are also given, okay. Then there is rectifier, that is ReLU, rectified linear unit, rectifier, soft plus. Okay, let's get to that. Now, so these are the important one, the sigmoid function, tan sigmoid function, step function. This is also step function, but here it's pointing towards 0, so there is no x value. And here there is the value of x. Okay. This is sine function and this is linear function. Here you can see there are different layers like hidden layer and input layer. Like first one is the input layer, second one is the hidden layer, and the last one is the output layer. And there can be multiple hidden layers. Okay, let's get back. Um, See, you can understand it using this. Here is your input signals. Okay. And they also have weights. Okay. So these are the weights W1, W2, and Wn. This is your summation junction where summation of Wi xi, where xi is your input value and Wi is your weight. This is your y sum. And then it goes inside the activation function. And then we get the y output. Okay. In this way, it works. Um, let's get back to a slide. Yes. Now, next is part 4, that is deep learning and cancer models. We will be covering this in our next session. So, till that, you can just go and through these concepts. And if you have any queries, so you can reach out us at biotechrebion@gmail.com. Yes. Yeah. So we will be meeting in the next session and we will be starting with deep learning concepts. So till then, stay tuned.